Welcome to The Debate. For decades, we've treated human nutrition like a simple combustion engine. Put in a certain amount of fuel, carbohydrates, fats, proteins, and just expect a perfectly predictable output of energy across the board.
Right. The classic a calorie is a calorie and a carb is a carb paradigm. It's clean, it's mathematical, and we've essentially built our entire public health infrastructure around it.
Yeah, exactly. But then we started looking closer. Specifically, we started looking at the trillions of microorganisms in the human gut. And suddenly, that simple combustion engine looks a lot more like a highly complex, highly individualized bioreactor.
Mm-hmm.
The fuel doesn't dictate the output anymore. The reactor does. And that brings us to the core of what we are examining today, which is the monumental shift from these universal one-size-fits-all dietary guidelines to precision nutrition guided by the human gut microbiome.
It is a massive shift. And today we're drawing on some really extensive clinical analyses, large-scale trials, and a very complex regulatory landscape found in the source material to ask a fundamental question. Are these microbiome-informed algorithms a mature, evidence-based science ready to revolutionize metabolic care? Or, and this is where I lean, are they a premature, heavily commercialized pseudoscience hindered by opaque models and marginal real-world clinical gains?
And that's exactly the tension here, because I will be arguing today that these microbiome-informed algorithms exhibit significant biologically plausible predictive power that effectively captures the complexity of metabolic responses that traditional metrics just completely miss.
Right. And I will be representing the skeptical view, arguing that these predictive models suffer from severe endpoint misalignment, deep methodological flaws, and frankly, a failure to demonstrate clinically significant superiority over standard healthy diets in the real world.
Well, let's dive into it. To begin breaking this down, I think we really have to acknowledge that generic metrics, like basic carbohydrate counting or the glycemic index, are fundamentally flawed
Flawed in what sense?
in the sense that they assume a universal physiological response that simply does not exist. And the foundational evidence for this, the data that really shattered that generic paradigm, came from the landmark ZV and Day 2 validation cohorts.
Right, yes. The 800-person cohort where they continuously monitored interstitial glucose levels.
Exactly. They captured the physiological responses to nearly 47,000 meals. And if you are listening and you've ever wondered why, your friend can eat a massive plate of pasta without gaining a pound while you look at a carb and gain weight, well, this study isolated exactly why.
The inter-individual variability was staggering.
It was. They gave healthy, non-diabetic adults a highly standardized meal, so a specific, uniform quantity of a bagel with cream cheese. For some participants, eating that exact bagel induced a negligible postprandial glycemic excursion, so a blood sugar spike of just 6 milligrams per deciliter.
Which is nothing.
Right, basically nothing. But for others, eating the exact same meal, the exact same bagel, the spike shot up to a severe 94 milligrams per deciliter.
I have to admit, seeing those numbers on paper, the variability is just striking. The idea that a standard bagel can act like a piece of celery in one person's bloodstream and a candy bar in another's is a profound biological insight.
It completely rewrites the rules. So to address this wild variance, the researchers developed a machine learning algorithm. They incorporated 16S rRNA sequencing of the gut microbiome, which is basically taking a genetic census of which bacteria are present in the gut.
Mm-hmm.
And they combined that with blood parameters and dietary habits. When they validated this in an independent U.S. cohort, this combined model achieved a predictive correlation for glycemic responses of R equals 0.62. To put that in perspective, relying on carbohydrate content alone yielded a correlation of just 0.40.
Yeah.
And if we briefly look at the PREDICT-1 study involving monozygotic twins.
Ah, right, the twin study.
Yes, it revealed something really remarkable. Host genetics play a surprisingly minor role in metabolic variant. When looking at postprandial lipemia, the fat levels in your blood after a meal, The microbiome accounted for 7.1% of the variance.
Right.
That is nearly double the influence of the meal's actual macronutrient content. So the microbiome isn't just background noise, it is the missing variable in metabolic care.
Well, I come at it from a different way. I will readily acknowledge the statistical predictability you're referencing in those highly controlled observational cohorts. I mean, the ZV study was a watershed moment for computational biology, no question.
Absolutely.
But we have to pivot to the profound limitations that emerge when we transition from these neat computational models to free-living clinical interventions. It is one thing to accurately predict a blood sugar spike on a computer screen. It is an entirely different thing to treat obesity or diabetes in the real world. And that brings me to the personal diet study.
Okay, which was a 6-month randomized controlled trial involving adults with obesity and abnormal glucose metabolism.
Correct. Participants were randomized to either a standardized, one-size-fits-all low-fat diet or a personalized, machine learning-generated diet based on their microbiome. Now, if the algorithmic approach is the revolution you say it is, it should easily outperform the generic diet.
Well, it depends on what you're measuring.
It failed to outperform it in the primary clinical endpoint. After 6 months, the standardized low-fat group achieved 4.31% absolute weight reduction. The personalized group, they achieved a slightly lower 3.26% reduction.
They failed to beat the standard diet.
And this highlights my core issue here. The commercialization of this science relies heavily on descriptive metrics like alpha diversity or mapping shifts in bacterial genera, rather than functional, hard clinical outcomes. It creates a severe misalignment between what the algorithms confidently predict and the actual health benefits delivered to the patient.
That's an interesting point, though I would frame it differently, because you are focusing on absolute weight loss as the sole arbiter of success. And metabolic health is, well, it's so much more nuanced than just the number on a scale.
Of course it is, but weight loss is a primary driver of metabolic improvement in these populations.
True, but in that very same personal diet study, let's look at what happened to the standardized low-fat group beyond the weight loss. They experienced a significantly greater decline in resting energy expenditure, a drop of 92.3 kilocalories per day, and they lost more fat-free mass.
Well, sure, but a drop in metabolic rate and lean mass is a completely standard consequence of hypocaloric diets. I mean, you eat less, your metabolism slows down.
Right, but a severe drop in resting energy expenditure and lean mass is the primary driver of adaptive thermogenesis. That is the exact physiological trap that causes massive weight regain after a diet ends.
I see where you're going with this.
Yeah, the fact that the personalized diet prevented this steep drop suggests it offers subtle but crucial protective metabolic effects during caloric restriction. The algorithm was optimizing for long-term metabolic resilience, not just starvation-induced rapid weight loss.
I'm sorry, but I just don't buy that framing, and let me tell you why. When we examine the clinical trials pushed by the commercial entities driving this field, the methodological flaws are just glaring.
Okay.
Take the method trial conducted by the commercial entity Zoe, which built upon the PREDICT studies you were just praising. They ran an 18-week randomized controlled trial comparing their personalized dietary program to standard USDA dietary advice.
And they reported a statistically significant reduction in triglycerides and improvements in body weight. I'd call that a successful trial.
Okay, let's look at the numbers. They reported a 0.13 millimole per liter reduction in triglycerides. Yes, it crossed the threshold for mathematical significance, but the clinical significance of 0.13 millimoles for actually altering a patient's long-term cardiovascular disease trajectory is highly debatable, if not entirely negligible.
It's still a positive directional trend.
But more importantly, and this is the crux of the issue, the trial utterly failed to isolate the intervention variable.
How so?
Well, the control group receives standard dietary advice via a static leaflet, a quick video, and a generic weekly email.
Right.
The intervention group, they didn't just get a personalized diet, they received an intensive digital health intervention featuring interactive app lessons, test foods paired with continuous glucose monitoring, and repeated behavioral coaching.
They received a comprehensive program to ensure adherence, which is necessary.
No, they received an intense behavioral intervention that the control group was completely denied. It's like claiming a brand new type of running shoe makes you run a faster marathon, but hiding the fact that the people wearing the new shoes also got a personal trainer yelling at them to sprint, while the control group just got a pamphlet on how to jog.
I think that's a bit of an exaggeration.
How can we possibly attribute the superior outcomes to the microbiome-informed algorithm when the sheer volume of behavioral support, tracking, and attention was vastly unequal? I mean, it is a textbook setup for the Hawthorne effect. People modifying their behavior simply because they are being intensely observed and coached.
Okay, I see why you think that. But let me give you a different perspective, using an analogy of my own. Think of these microbiome algorithms like a highly precise meteorological model.
Okay.
The algorithm looks at the atmospheric pressure, the humidity, or in this case, the microbiome and the metabolome, and says it is going to rain at exactly 2 p.m. Now, if a user gets that forecast, ignores it, walks outside without an umbrella, and gets wet, we don't say the weather model is mathematically flawed. We say the behavioral adherence failed.
But
The difficulty of proving clinical superiority in a free-living trial, where you often have to use intense behavioral support just to get humans to follow a diet, that doesn't invalidate the predictive accuracy of the algorithm itself.
a weather forecast doesn't require FDA approval to claim it can treat metabolic syndrome. If you are selling a medical or nutritional intervention, you have to prove that the specific mechanism you are commercializing is the active ingredient.
It is the active ingredient.
If the active ingredient is actually just the continuous glucose monitoring and a health coach cheering you on through a slick app, then the microbiome sequencing is just expensive theater.
It is absolutely not theater, because the predictive power of these models is backed by irrefutable biochemical mechanisms. We are not just looking at statistical noise or behavioral placebos here. We are tracking precise biomolecular pathways.
Yes, the biochemistry exists, but
When diets high in ultra-processed foods compromise the intestinal mucosal barrier, lipopolysaccharides enter the host cycle and trigger metabolic endotoxinium. This actively drives insulin resistance. But if a personalized diet can foster specific taxa, we see direct protective effects. Take a specific bacteria, Akkermansia muciniphila.
a very popular microbe in the literature right now, yeah.
For good reason. We know it produces a specific outer membrane protein called AMUC1100. Now, how does this work? Think of the PK-BK-ASE pathway, like the master switch for insulin in your cells.
Mm-hmm.
When that switch is flipped, your cells can effectively absorb glucose from your blood. This AMUC1100 protein specifically activates toll-like receptor 2 signaling pathways, which essentially guards this master switch. It ensures your body stays sensitive to insulin even if your diet isn't perfect. So by maintaining this critical node, the microbial protein actively improves insulin sensitivity.
I don't dispute the biochemistry. I really don't. That Akkermansia or, short-chain fatty acids like butyrate and propionate have profound systemic effects on GLP-1 secretion and glycemic responses, established science.
Exactly. Or take trimethyl N-oxide, TMAO, which does the exact opposite by blocking that same insulin signaling pathway. The metabolic pathways aren't just magically correlated, they are mechanistically established.
They are. But that is a compelling argument that completely sidesteps the actual computational problem we are dealing with. Have you considered how the commercial algorithms actually operate? Because they do not neatly trace these biochemical pathways step by step.
They model the complexity of them,
They rely on opaque black box machine learning models, specifically things like random forest and extreme gradient boosting, or XGBoost.
which are highly sophisticated ensemble tree-based models perfectly suited to handle nonlinear biological data.
Suited, perhaps, but deeply flawed in this context. In microbiome research, datasets are extraordinarily high-dimensional and, mathematically speaking, quite sparse.
Explain what you mean by sparse in this context.
Let me explain what that means. A single stool sample generates thousands of taxonomic features, different bacterial strains, species, genes. Yet the clinical cohorts for these studies are relatively small, maybe a few hundred patients.
Right, which is why the AI is necessary to find the patterns a human couldn't possibly see.
But it creates what data scientists call the curse of dementiality, When you have 10,000 bacterial variables in only 100 patients, the math essentially guarantees that the AI will find a pattern, even if it's completely false.
I think guarantees is a bit strong.
These models are highly susceptible to overfitting, capturing random noise rather than true biological signals. A random forest model might identify a specific, rare bacterial genus as a strong predictor for poor glycemic control in a training cohort. But the black box cannot tell you if that bacteria caused the metabolic dysfunction or if the host's terrible diet simply created an intestinal environment that favored that bacteria. Correlation is masquerading as causation. Descriptive metrics are being sold as functional drivers.
I'm not convinced by that line of reasoning because the field is already aggressively addressing the black box problem. We are transitioning toward explainable AI, specifically using SHAP values.
SHAP, right?
Yes, shapely additive explanations. Instead of a black box just spitting out a final answer, SHAP deconstructs the output of the model. It quantifies the exact directional impact and weight of every single feature on a specific prediction.
It's still analyzing a correlative model, though.
But it tells you why the AI made the choice it did, transitioning it from a purely predictive engine into a transparent hypothesis-generating tool. But even beyond that, how do you respond to the development of genome-scale metabolic models, or GSMS?
You're referring to resources like Agora 2.
Exactly. Agora 2 encompasses highly curated, strain-resolved metabolic reconstructions for over 7,300 human gut microbial strains. This isn't the statistical pattern matching you're criticizing. This is deterministic, mechanistic modeling built on fundamental thermodynamic principles.
I am familiar with it.
With Agora 2, researchers can build a microbial digital twin of a patient inside a computer. They can computationally simulate feeding this digital microbiome a specific dietary substrate, like inulin fiber, and mathematically calculate the exact output flux of short-chain fatty acids. Doesn't this bridge the exact gap you are criticizing between statistical correlation and biological causation?
It absolutely does. Agora 2, flux balance analysis, mechanistic modeling, this represents the true science of personalized nutrition, and I have immense respect for this work. But let's be very clear here. This is not what direct-to-consumer companies are currently scaling and selling to the public.
Well, the market takes time to catch up to the cutting edge.
The true science is computationally massive and requires vast amounts of curated biochemical data. The commercial entities are exploiting a temporal gap between rigorous academic modeling and consumer desperation.
You feel the commercialization has aggressively outpaced the clinical validation?
It is worse than that. It is actively exploiting regulatory loopholes. In the United States, many of these tests operate under CLIA as laboratory-developed tests, or LDTs.
Right.
By categorizing their products as wellness tools rather than diagnostic medical devices, they entirely bypass the stringent FDA pre-market efficacy, clinical validity, and safety requirements. There is no uniform consensus on what constitutes a healthy microbiome under CLIA proficiency testing.
That's a regulatory issue, not a scientific one.
But the result is that consumers are being prescribed highly specific dietary restrictions and being sold expensive monthly supplement subscriptions based on proprietary algorithms that are completely shielded from peer-reviewed scientific auditing.
Okay, I will concede that the direct-to-consumer market can be premature in its marketing claims. We see that in almost every biotech frontier. However, we cannot throw the baby out with the bathwater by labeling the underlying biomolecular technology as pseudoscience.
I'm not calling all of it pseudoscience, just the premature dietary applications.
But let's look at Viome, because you're assuming the technology is static. You're talking about standard 16S RNA DNA sequencing, which, yes, just takes a census of what microbes are present. But the field has already moved to metatranscriptomics, or RNA sequencing.
Right.
This doesn't just ask who is there. It catalogs the genes that are actively being expressed by those microbes in real time.
Which is biologically superior. Yes, reading the active RNA tells you what the bacteria are actually doing, not just that they exist. But their dietary application still relies on internal AI algorithms lacking independent RCT validation.
But look at what that exact same metatranscriptomic technology just achieved in a different domain, Viome recently received an FDA breakthrough device designation for Cancer Detect.
I saw that, yeah.
It's a saliva-based test for oral and throat squamous cell carcinomas. By analyzing salivary RNA markers, essentially listening to the active genetic chatter of the mouth's microbiome, the test achieved approximately 90% sensitivity and 95% specificity that vastly outperforms conventional clinical exams.
It's impressive.
This proves that the underlying technology, reading microbial RNA to predict host health states, is rigorously valid and passes the highest regulatory bars. The dietary applications are simply on a slightly longer developmental curve, but the foundation is rock solid.
I agree that the biomolecular technology itself, the RNA sequencing, is rigorous. The pseudoscience label applies to the unvalidated extrapolation of that technology into commercial dietary algorithms. Identifying a cancer biomarker is a binary, diagnostic endpoint.
Sure.
It's a yes or no question. Is cancer present? Modulating a highly dynamic trillion-cell ecosystem to cure obesity while competing with the patient's lifestyle, sleep, stress, and behavioral adherence, that is a completely different universe of complexity.
It is profoundly complex, which is exactly why we need these high-dimensional models, rather than relying on a static food pyramid that treats everyone identically.
But until those high-dimensional models are subjected to independent, third-party, double-blinded clinical trials that actually control for the Hawthorne effect, trials that don't conflate intense behavioral coaching with algorithmic efficacy, claims of clinical supremacy remain scientifically tenuous.
Well, let's pull this together. In summary, my position is that microbiome-informed algorithms represent a massive leap forward. As we saw with the bagel response, they genuinely outperform generic dietary heuristics in predicting acute postprandial metabolic responses. The foundational science detailing how the microbiome mediates energy metabolism via specific enzymatic pathways, whether it's SCFA production, guarding insulin sensitivity, or TLR2 activation, it is biologically irrefutable. We are moving from simply observing phenomena to mathematically simulating them with tools like Agor2. This technology isn't a fad. It represents the undeniable future of targeted metabolic care.
And my conclusion is that while the biological mechanisms are undeniably fascinating, translating acute predictive capabilities into long-term clinical superiority is exceedingly difficult. The physiological noise of human behavior often drowns out the marginal gains provided by algorithmic precision.
Right.
Until these commercial models move away from correlative black box machine learning, where they fall prey to the curse of dimensionality, and prove themselves in rigorous trials that isolate the dietary intervention from digital coaching, we have to be honest with patients. Universal dietary fundamentals, maximizing dietary fiber, minimizing ultra-processed foods, and maintaining caloric balance, these remain the most clinically effective interventions for the general population.
I think where we absolutely converge is on the necessity for the field to mature computationally. The transition from correlative prediction to mechanistic simulation, utilizing frameworks like microbial digital twins, is exactly what will fulfill the promise of personalized nutrition. There is clearly much more to explore in the source material regarding how we regulate and validate these tools as they evolve.
Agreed. The science is real. It is the commercial application that requires our utmost rigor.
So, we return to our initial thought. The human body is not a simple combustion engine, blindly processing whatever fuel we dump into the tank. It is a highly dynamic bioreactor teeming with microscopic life that actively dictates our metabolic fate. The challenge moving forward isn't just mapping the reactor, but learning how to responsibly and effectively pull the levers. Thank you for joining us on the debate.